Hello there, Mr. Sutton here, bringing you this Pre-Cal Honors 9.5 lesson on limits at infinity. In this one, we will find limits algebraically of polynomial and rational functions and a whole bunch of other ones at infinity. As a little side project, we will also find some horizontal asymptotes. For our warm-up, let's say we have some positive constant c. See if you can figure out what these expressions with infinity ought to come out to. Alright, so let's take a look at what we have here. Infinity is endlessness, so if you add a constant, subtract it, multiply it, or divide by a constant, in all of those cases, you're going to end up with just more infinity. Same thing if you take an infinity and just keep multiplying it by itself. Here's where it gets a little interesting, though. If you multiply by a negative, you can change the direction of infinity to be negative. And if you square a negative infinity, it follows normal sign rules and becomes a positive infinity. Now here's where it gets even more interesting. If we take a constant and divide it by infinity, well, if your denominator is getting larger and larger and larger, that means your whole fraction just keeps shrinking until you eventually get to 0. Here's where it gets even more interesting. If we take an infinity and divide it by itself. Unfortunately, the answer to this is not just 1. That would assume that these were the same value. But infinity doesn't really have a value. And there are different kinds of infinities. There are an infinite number of integers. There are an infinite number of fractions, but I think we can agree there's more fractions than there are integers. So this is actually indeterminate. We don't really know what it is. We have to do more work. Same thing if you have an infinity minus an infinity, also indeterminate. Can't really figure it out what it is without doing more work. So the good news out of all this is that we can plug in and evaluate expressions that have infinity in one place. But the bad news is we can't really consistently handle more than one infinity at once. So a lot of this lesson is really just about getting it down to a single infinity in each problem. At this point, we're going to dive into applying the concept of infinity to algebraic limits. So if you just go ahead and plug infinity in like we do normal constants, we quickly run into a problem here. Infinity minus infinity is no good. We've seen this. So what do we do instead? We're going to use something called the principle of dominance here, which says that at infinity, we only consider the fastest growing term. This x to the fourth is our fastest growing term. This is affecting the end behavior of this function, which is what infinite limits are talking about. All these other terms might matter at finite numbers, but at infinity, we don't really care about them. So we can rewrite this whole thing then as just limit as x approaches infinity of x to the fourth. And at this point, after you have eliminated the slower growing terms, you just plug infinity in and evaluate. One infinity, we can deal with that. So this is just infinity to the fourth. A bunch of infinities multiplied together just gives you infinity. Alright, pause the video and see if you can take this one on. Alright, so hopefully you noticed that the fastest growing term on this one was hidden in here, this x to the fifth, a little bit sneaky there. So we're going to rewrite this as the limit as x approaches negative infinity of negative x to the fifth. Plugging negative infinity in there now, we get to use some sign rules. Negative to an odd power just gives us another negative, negative infinity in this case. Multiplying that by the negative out here, we now have a positive infinity. So one little thing before we leave this page, and that is to remember that you can't ignore terms with finite limits. This only works with infinite limits. For our next example, we're going to take a look at an infinite limit for a rational function, a quotient of polynomials. Now we still care about who's growing faster, but in this case we care about whether it's the numerator or denominator. And there's a whole bunch of terms in the numerator and denominator, so before we do anything else, we're going to start this problem by doing what I like to call choosing your champion for each side of the fraction. Choose the fastest growing term on each side. So it's kind of like in ancient times when there were two armies squaring off and you just pick your biggest and baddest guys to go fight each other. So pause the video and get rid of everything that's not the biggest term in the numerator and denominator. So hopefully you rewrote this as limit as x approaches negative infinity of 3x to the fourth over 8x to the fifth, because those are the fastest growing terms on the top and the bottom. At this point, once you've chosen your champions, if it's just a rational function with polynomials, we're just going to reduce and plug in. So in this case, these x's can cancel for the most part. We have a 3 left on top and just an 8x to the first power in the denominator. And at this point, we're just going to plug that negative infinity in here. Now, you might remember from our discussion earlier that if you're dividing a constant by essentially infinity, that ends up being 0. And that's exactly what our limit is here. Here's another rational function for you to try. Pause the video and give it a shot. All right, so in this one, the fastest growing function up top is 5x to the 9th. On the bottom, it's 15x to the 9th. And in this case, if we reduce, we can actually cancel these x's out completely, and this just reduces to 1/3. For our last regular example, we're asking where this crazy-looking function has a horizontal asymptote. Now, there's a whole bunch going on in this problem, but let's start with the type of problem. If we're asking about horizontal asymptotes are going to happen where your function is approaching infinity or negative infinity. Again, we're asking as you go to the far left or the far right, is there a number that you're kind of gravitating towards? So that means we're going to have to take the limit as x approaches infinity of this function up here. We're also going to have to take the limit as x approaches negative infinity because sometimes it's different. But let's deal with positive infinity first. So pause the video and see if you can figure out the fastest growing function on each side. Choose your champion. All right, so for the numerator, we have e to the x versus ln of x. Now, you might remember that e to the x, this is an exponentially growing function, which is pretty fast. ln, that's logarithmic growth, which is pretty slow. So between the two of those, e to the x is definitely going to grow faster. In the denominator, it's a little bit easier because we just have power functions here. X to the 100th is definitely faster to anything to the 99th. So at this point, we can't really reduce this like we did the rational functions. These are not the same base. So what do we do instead? When you have fractions with non-polynomials, we're going to use top-heavy versus bottom-heavy reasoning, kind of like you did with rational functions when you learned about them in pre-calculus. So is this a top or bottom-heavy function? Which one is growing faster, e to the x or x to the 100th? If you think about it, exponential growth is faster than polynomial growth. So this is a top-heavy function, which means that we're not approaching a single finite number. We're just growing without bound toward either infinity or negative infinity. And the direction is going to just depend on the signs of the things in your quotient here. Since these are all positive quantities, this is going to be a positive infinity that this is growing towards. Now, positive infinity or negative, either way, in terms of asymptotes, that means that you have no horizontal asymptote if you have an infinite limit. So as we move to the right, there is no right side horizontal asymptote. So we're going to keep going on this problem because we also have to figure out the limit as x approaches negative infinity. So the key on this one when you're picking your faster growing functions, x to the 100th on the denominator is definitely still going to be faster, but in the numerator it's a little bit different because this is an exponential function, e to the x, and when you have a negative exponent, which is what happens when you plug negative infinity in here, exponential functions with negative exponents are actually decay functions, and they always decay to 0 in the long run. So if we have a function that's decaying to 0 and a really slowly growing function, we're going to have to go with the slow grower here, ln of x. So here are our champions for this battle. And between the two of them, I think we can agree that x to the 100th blows ln of x out of the water here. So this ends up being a bottom-heavy function, which means our denominator is growing much faster than our numerator, so our fraction is getting smaller and smaller all the way to 0. So this limit then is going to be 0, which means we have a horizontal asymptote at y equals 0. And this is a left horizontal asymptote because we were going to negative infinity when we found this. For a wrap-up, just as an extension of that last problem, I've given you a whole bunch of functions here of different types. Your job is to place these in decreasing order of dominance from strongest to weakest. Pause the video and give it a shot. All right, let's see if we had the same order here. So the strongest function out of all these is this x to the x function, the tower function. If you think about what this is doing, let's say you're plugging in 10, you're really taking 10 tens and multiplying them together. Now, not quite as strong, but almost as strong as the tower function is this next one, this x exclamation mark. This is x factorial. This would be like having 10 times 9 times 8 times 7. Still pretty good. right below that is just a normal exponential function like e to the x. So this is taking, say, 10 of these e's and multiplying them together. And then below that, we have the highest polynomial in this list, x to the 1000th, followed by x squared, and then just plain old x. Now, between all of these, the square root of x is still growing a little bit faster than ln of x. I mean, think about the square root of 100 is 10 versus the number I have to raise 2.72 to get 10. It is less than 10. So square root of x is going next. And then ln of x is at least growing. And then we saw before that e to the negative x, this is actually decaying. So that would be the weakest out of this list. So until next time, this is Mr. Sutton signing off.